Good morning, everyone. My name is Jie. Now I'm a doctoral researcher in Aalto University, and today I'm going to talk about crossing the simulation experiment gap using style translation for enhanced atomic structure discovery from AFM images. So let me get started with the structure discovery and its challenges. So we want to see the atoms, so we can take photos using atomic force microscopy. So unlike the usual photos, we are not recording the light intensity. We encode the force information, and also we can move the tip around along the z-axis so that we can get slices of images. So, but we can take photos of these samples, but to interpret these images is still challenges. We don't exactly know what is the atom located or what is the configuration of it. So it seems pretty difficult to do this structure discovery only by looking by using our eyes. So instead of using by eyes, we have developed some tools like using per particle model, which is a simulation tool, so that we can simulate the AFM images. So the input of this model is atomic configurations. So since this we have this simulation tool, we can generate lots of image and lots of simulation image and its corresponding atomic configurations. So it makes possible that we can learn inverse map from the simulated images to the atomic configurations. So we have done that in our previous work, and then this as after we train this model, we input in the AFM images, we can get the atomic configuration. But our final goal is not only on this simulated images. We want to input the real experimental images to our model and make it predict. So as you can notice, there's a gap between this simulated images and experimental AFM images. For example, there are some noises in the simulated images. So we believe that this kind of gap will block the performance of the machine learning models. So a natural question is that whether it's possible that we can train a model directly on this experimental AFM images. It's almost impossible for two reasons. The first one is it costs a lot to generate a lot of experimental AFM images. But a more critical point is that even though we can have a lot of experimental AFM images, we do not know the exactly atomic configuration. So it means that we cannot train this model because we lack the label of the AFM images. So in the following talk, I'm going to try to explain how we try to crossing the gap between the simulation. So we believe that if we want to train a useful machine learning model to discover the structure, we should make this training data more realistic to make it more like more like experimental AFM images. So this is our simulation data set, which is water molecules on gold surface. And then we do the simulation on structures, and we can get the simulation AFM images. And then we do style translation on this simulated images to make it more realistic. So this is this style translation method is a neural network, so it learns from experiment. So how can we achieve this style translation? We use a framework called CycleGAN. CycleGAN learns the map between two domains. without paired training data, which means to train this framework, we need to what we need to do is collect two sets of data, one from simulation, another from an experiment, so that after trained, it can do the style translation. So for example, this is some pictures from CycleGAN paper. We input zebra image, it will output horse image. So the interesting part is that this model learns where to make modification and keep the irrelevant part the same. So this is the things we like, because we don't want the model to change too much about our simulation images, because that will lose some physical meanings. So we have applied this in our work. So here is the result. The first column corresponds to the simulation image, and then the second column is the style translated image. So it learns some experimental style. I hope you can see. So it adds some noises in the background, and also not only we can get the forward translation, but also we can also get this reverse translation from experiment to simulation, so that it serves as denoising tools, and also it can remove some artifacts. To evaluate this the style translation performance, we do a simple task. We train machine experts to tell whether a given image is real, or a given image is from simulation or from experiment, and the output value is just a number, and we use it as the fidelity of a given image. And we input the simulation images to this machine expert. It will get a distribution look like this. And then when we input this experimental images, and it will generate a distribution look like this, which means from this images, we can see that this machine experts can learn to distinguish between simulation and experimental AF images. So what we do here is we started with the simulation images and do the style translation to this image, and it will end up with the distribution look like this, which means that we started from this distribution, which is mostly from the simulation distribution, and then we can get a distribution like this, which is more close to the real data. So here we believe that using this generator from CycleGAN, we can crossing this simulation and an experimental gap. And then let's look back into this framework. And then here we use CycleGAN to do the style translation. And we talk about it's almost impossible to train on the real experimental data. But if we can, like here, we can do the style translation to it, we can get a experimental-like AFM images. And we use this as replacement to the real experimental data. So the advantage here is that not only we can have this experimental style images, we can also have its enable the atomic configuration, because all of this is coming from the simulation. So that it's possible that we can train a model on this experimental style AFM images. And we have done that. And here is the result. So this is the experimental images. And then the first column corresponds to the prediction of the model trained only on simulation images, and the following three columns correspond to the models trained on style translated data sets. And here is some more complex structure. As you can see from this picture, for example, maybe you can, by looking at this, we may say that maybe this one is more close to the experiment, but this is just by looking by our eyes. So a question is that and for this experimental images, we still don't know what is the right answer. So in this case, if we don't know the answers, how can we tell whether predictions are good? So, so we have tried to doing this thing. We calculate some theoretical local structure distribution obtained from simulation. So we calculate some oxygen-oxygen distance and OH bond distance, and also some angles, and also some free OH bond at the surface, and also the hydrogen bonds related property, and also calculate some other parameter, and so um, which compute the distances from a reference structure. So then we get this, and we believe that the good prediction of the atomic structure should be consistent with this theoretical local distribution. So we indeed our structure discovery model to predict the structures, and then we also calculate the corresponding distributions. Then we calculate the distance between the reference distribution and the predicted distribution, and here is our result. So this blue bar corresponds to the model trained only on the simulation dataset, and this red bars correspond to the models trained on style translated datasets. So as you can see from this sex properties, this the distance from our reference distribution is for this model for this model is lower than the model trained on only on simulation datasets. So which means that by using this style translated dataset, we can have a better prediction of the experimental AFM images. So let's bring to my conclusion. So in this work, we want to make structure discovery from AFM images more reliable, especially using the real AFM images. And we believe machine learning can help us to achieve this goal, but only if it learns from the right data. So we use the style translation to translate the simulation images to more realistic experimental images, and then we're using it to train the machine learning model, and we find it can predict a better prediction, and then it makes AFM images interpretation more reliable. So I think this is a step closer to automated atomic level discovery. And in the future, maybe Bayesian optimization can also be applied to tune the hyperparameters, and also some diffusion-based model can also be used. So now I'd like to thank all the colleagues in my group, and also the previous work of PBFM, and also some colleagues, and also the funding, and also the computational resources, as well as the organizers of this conference. And thank you all.
Thank you very much for your talk. Are there any questions from the audience?
Thank you for the nice talk. So I assume that to train your cycle GAN, you still need a lot of measured AFM images, right?
Yes.
So is that better than directly going from the AFM image to the atomic structure, which you said was very difficult or impossible because of the data requirement, but the cycle GAN has a lower data requirement, or am I missing something?
So to train a structure discovery model, we need both the image and also the its label, atomic configuration. So if we get the images from experiments, we only know the image itself, but we lack the label. So, which means it's impossible to train. But using CycleGAN here, we can turn a simulation to experimental-like AF images so that we know the atomic configuration. So it makes this training possible.
Okay, but for that, you still need the experimental AFM images.
So in the training phases, we don't need it. But our final goal is when testing phase, we feed the experimental images to our model to make it predict.
Okay, we can talk later.
Thanks.
Hi, thank you for the talk. So here I see there's two ways now. So you've completed the loop from atomic configuration to experimental AFM. So couldn't you just now use CycleGAN from experimental images to get to simulated images, and then you already have this FU transformation that you said previously done? So can't you, in that way, generate these kind of quote unquote labels for the experimental ones already?
Yes, we can do. For example, here's like a two ways. If you have you can get a generator from simulation to experiment, and also at the same time you get a reverse, like a reverse style translation from this. So in principle, you can by when you're predicting an experimental image, AF images, you can use this path to translate experimental AF images look like simulation, and then using a model trained on the simulation data set and to make it predict. We have tried this way, but the performance is not really good compared to this way.
Okay, thank you.
Thanks for your question.
Thank you for a great talk. I'm wondering, did you measure the domain gap and to what extent this CycleGAN can work? For example, some robustness analysis to see if we have a greater domain gap, can it capture the translations and so on?
So here we have used this to like a pre-evaluation the quantity of the style translated images. So here is that we try to we first build a machine expert to tell whether whether images come from simulation or experiment, and then here. So if the images come from simulation, it will get a distribution like this, and then we input the same images to the style translation generator, and then it will get a distribution like this. So to some extent, this curve shows that it can have the ability to push a distribution like this, so then it can push like a simulation distribution to a real experimental distribution. I'm not sure whether I answered the question.
Partly, but okay, it's okay. For example, this is an end-to-end approach, or have you considered, for example, doing this fully end-to-end without the two-step learning process? Jointly optimizing.
So this the CycleGAN here is a independent framework, and then we have done this part, and then we train this structure discovery model. So it's not like a not very end-to-end model.
Okay, thank you.
Thanks.
Jie, my question is, with the output of these models, what are they actually doing with them? And is the uncertainty that you're seeing, is it useful, or is there too much uncertainty, right? Because it's a stochastic process. If you were to repeat this multiple times, you don't get the same structure every time, and there still looks like there's a fair bit of variability. So is it good enough to do something with it?
Yes. So there's some. For example, for this given image, the structure discovery can output image like this, but for example, if we rotate this image, it will generate. So ideally, it will generate just the rotated images, but actually, so it is slightly different from this. So we try to make it this structure discovery model can handle the like a rotation or something like that, but we're still working on it.
I think we can now thank our speaker again.
Thank you very much.
And now I would like to invite everyone for a lunch break.